All right, in this lecture, we're going to take a look at the bonding within organic molecules. And to be perfectly honest, there really isn't any one theory that works perfectly 100% of the time. And so, simply just because organic molecules tend to be massive, they tend to be huge. And so what we do as organic chemists is kind of take from both prevalent bonding theories and kind of mishmash them together, take from one, take the other, and have, use something that kind of helps describe bonding in organic chemistry the best. And so the two theories we're going to look at and combine together are valence bond theory and molecular orbital theory. Both of these are generally covered in general chemistry, so I'm going to quickly kind of review them and then we'll dive a little bit deeper into how these two things are combined. So valence bond theory basically says that a bond is formed or a bond is consists of um, is a sharing of electron density between two atoms. Now, I kind of want you to circle, highlight, star that word between, because that's going to contrast a whole lot with molecular orbital theory. So the example that you see here, we're taking two hydrogen atoms or 1s atomic orbitals, and they combine, they are sharing their sole electron with each other to form a bond between them. And again, I want to emphasize these electrons are localized across just those two atoms. And this forms what is known as a sigma bond. We'll use the Greek letter sigma to denote that. And I'll go a little bit deeper about like what is actually a sigma bond, but kind of the simple thing to remember is that all single bonds are sigma bonds. Now let's contrast that with the other prevalent type of bonding that occurs, or that I should say, bonding theory that we use to describe how atoms bond in organic chemistry, is molecular orbital theory. Molecular orbital theory will take atomic orbitals, and they are mathematically combined to make molecular orbitals. And you'll see me use the uh, shorthand MOs for molecular orbitals. Now, here's how this is different. Atomic orbitals are associated with an atom. Molecular orbitals are associated with an entire molecule. And this is where the two theories differ. A valence bond theory will say that the electrons in a bond are shared between two atoms and no more. Molecular orbital theory says, well, those electrons could be shared across multiple atoms or even across an entire molecule. And so there's that's the main difference that I want you to know between those two theories. So if we look at a hydrogen molecule, what we're going to do is take, so here's one hydrogen, here's the other, and they're in their 1s orbitals. And we're going to take those two atomic orbitals, one from one hydrogen, one from the other, and we're going to combine them together to make two molecular orbitals. So that's an important thing to remember. The number of atomic orbitals equals the number of molecular orbitals that gets formed. Now, for hydrogen, one of those molecular orbitals will be much lower in energy than the other molecular orbital. Now, one thing I want you to get in your minds now when we talk about energy and stability is that molecules will seek to be the most stable version of themselves as possible. They want to have a low energy. It's not advantageous to have a lot for a molecule to have a lot of energy. So notice what this in this diagram, we take these electrons in the 1s orbital and we put them both in the what we call the bonding molecular orbital. It's a low energy molecular orbital. And you'll notice that like the electrons are represented by this kind of cloud here. So electrons are spread out, delocalized. We like that. That gives a lot of stability if electrons are kind of spread out. Now, the molecular orbital that's higher in energy, we call it an antibonding molecular orbital. You'll notice that the electrons are either over here or over here. There's a region which we call a node that there isn't any electron density. So the electrons are less delocalized in antibonding molecular orbitals than they are in non-bonding, or I'm sorry, in bonding molecular orbitals. Now, the rules for filling up molecular orbitals is exactly the same as filling up atomic orbitals, like what you did in general chemistry. So we always start at the lowest energy level, and at most, we can put two electrons in one orbital, just like you did in general chemistry. Now, I'm going to highlight a couple of points now. We're going to kind of put them away, and then we'll bring them out periodically when we start talking about chemical reactions. But generally, there might be a lot of molecular orbitals for a molecule. Sometimes we only care about a couple of them. We call these molecular orbitals, first of all, this one here, we call it the highest occupied molecular orbital. We'll use the acronym HOMO. So if we just break that name down, it's the molecular orbital that's highest in energy, but still has electrons in it. So when we say highest occupied, it's the molecular orbital with the highest energy that has electrons, and that's what's represented there. This orbital right here has electrons in it. Now, the next one that we like to look at is what we call the lowest unoccupied molecular orbital, also known as the LUMO. And again, if we break the name down, that is the molecular orbital that has the lowest energy but is unoccupied. It's got to fit both of those terms there. Lowest energy, but it's empty. And the reason I'm pointing these out now is because when we start talking about how organic molecules react, we're going to be looking at how the highest occupied molecular orbital of one reactant is going to interact with the lowest unoccupied molecular orbital of a second reactant. And kind of, think about it that way. You have electrons that will want to fill an empty orbital. So that's why we use the HOMO of one reactant and see how it's going to interact with the LUMO of the other reactant. All right, so let's talk a little bit about hybridization and how we use hybridization to describe bonds in organic chemistry. Now, again, hybridization is one of those concepts I believe that is covered in general chemistry. You might remember things like sp3 and sp2 and or sp3d or all of those types. We're going to focus on just a few of those hybridizations because we're dealing with carbon. There's really very limited types of hybridizations that carbon will have when it bonds with other atoms. Now, where does this concept of hybridization come from? Let's just take the simplest organic, or one of the simplest organic molecules, methane, and look at the CH4. Now, if we go all the way back to general chemistry and Vesper theory, which I'll talk a little bit more about, if we look at that carbon atom, that carbon has four regions of electron density. So if I were to ask you, well, what's the molecular shape around that carbon? You would say, well, it's tetrahedral. And then if I were to ask you, well, what are the approximate bond angles around that carbon? You probably would say like about 109.5. That's kind of like the magic number that you memorized for an carbon that was tetrahedral. Um, Now, here's the problem with this. I want you to think back to electron configuration. We're going to do the electron configuration for carbon. We have the 1s orbital, 2s orbital, and then the 2p orbitals. Okay, so think about what that means in terms of the p orbitals. How are those p orbitals arranged in relationship to each other? Well, you had a px that would lie on the x-axis. You'd have a py that would lie on the y-axis. And then you'd have pz, just pretend that that's coming out at you, along the z-axis. And that would literally form an axis like this. So you have your x, your y, and your z. I want you to think about this answer in your head. What are the bond angles of those three axes to each other? X to y, y to z, or x to z. What are the bond angles of, or I want to say not bond angles, but angles? So they're all perpendicular to each other. Angles are 90 degrees. So how is it that an atom that's got two p orbitals, where those p orbitals are arranged in 90 degrees, how is it that when it bonds, now they magically, quote unquote, have a bond angle of 109 degrees? That doesn't make sense. So scientist named Linus Pauling kind of came up with an alternative to this. He basically said the electron configuration of carbon in a molecule doesn't have to be the same as a free carbon atom. Whenever you did electron configuration in GChem, you always just dealt with free atoms. You never really associated with them. What Linus Pauling was saying is that the if a carbon atom is bonding to other things, it doesn't necessarily have to have the same electron configuration. And this is where the concept of hybridization came about. And so let's talk about the types of hybridization that's important in organic chemistry. So what we're going to do is take the valence shell of carbon. Now we're just going to focus on that. So I'm going to redraw those here. Here's 2s, and here's our 2p. Now I'm going to stick all of those orbitals, not just not the electrons, but I'm going to stick the orbitals in what I'm going to call a hybrid blender. We're going to hybridize them. And when that blender is done, you end up with four four sp3 hybrid orbitals. And since I started out with 4 electrons in the valence shell, I'm going to put 1 electron in each of those hybrid orbitals. Now, another important thing I want to point out is that all 4 of those hybrid orbitals are equal in energy. Remember the term that we use for that in general chemistry? We call them degenerate. They're all equal in energy. And by blending those two orbitals, the 2s and the 2p's, blending them all together, kind of change the shape a little bit. But you'll kind of have like a small end to the sp3 orbital and a larger end. So that's what our hybrid orbitals are going to look like. So that now, since the shape is different, the energy is different, then those hybrid orbitals will spread out to give us that magic 109-degree angle for an atom that has four regions of electron density. So if an atom like methane has four regions of electron density, its bond angle will be around that 109, and its shape will be tetrahedral. Now, in our next lecture, I'll kind of talk about what happens when there's lone pairs, because then it doesn't necessarily become a tetrahedral shape. It could be um, um, trigonal, bipyramidal, or bent. I'll talk more about that, in our next lecture. But just to show some more examples of atoms that have this sp3 hybridization. So like ethane here. All right, these carbons are both sp3 hybridized. They have four regions of density around them. So that's an important trend that you should know. If you see an atom with four regions of electron density, especially carbon, we're dealing with we're focusing on carbon, then four regions of electron density would make it a sp3 hybridized atom. Or, for example, oxygen. Oxygen has, in this case, two pairs of bonds, two lone pairs, still four regions of electron density. So we would call that an sp3 hybridized atom. If I'm going to kind of draw this bond, I'll focus on this carbon-carbon bond here. I'm going to kind of show that orbital overlap like this. This is the sp3 orbital of one carbon overlapping with an sp3 orbital of another carbon. How would I do this for hydrogen? So let's say there's a hydrogen atom out here. Well, here's another sp3 hybrid orbital. It's going to overlap with an atomic orbital, because that's what all that hydrogen really is. It's just a 1s atomic orbital with one electron in it. And this gets us to kind of like our true definition of what a sigma bond is. A sigma bond is a head-to-head overlap of an atomic orbital with a hybrid orbital. Or another case for this, the overlap of two hybrid orbitals. Doesn't matter what kind of hybrid orbitals they are. They could be sp3 orbitals overlapping head to head. They could be, and we'll get into sp2 in a little bit, but sp3 with an sp2. So any hybrid orbitals overlapping, or if it's a hybrid orbital with an atomic orbital, that classifies as a sigma bond. So I'm going to go back up here. We can see that is the case here with a carbon-carbon bond. That's a sigma bond. And a carbon-hydrogen bond where you have an sp3 orbital overlapping with a 1s, that's also a sigma bond. All right, let's go to our next hybridization. Now, if we take our valence shell, again, we're looking at 2s and the two p's, we take all of those, throw them into our hybrid blender, and it only spits out three hybrid orbitals. Kind of like, when you're making a smoothie in a blender and it doesn't blend all the way, you still have like chunks of fruit kind of floating around. Um, in the case of this, where you only get three hybrid orbitals out of it, there will be one unhybridized p orbital left. Now, that's not a bad thing. That's actually very important in describing multiple bonds in organic molecules. Now, like sp3, these sp2 orbitals are degenerate. They're all equal in energy. And the unhybridized p orbital is higher in energy than the sp2 orbitals. So we're going to look at this compound as an example here. This is ethene, or also known as ethylene. And what I want you to do is look at any of the carbon atoms and count the regions of electron density. Keeping in mind, you treat a multiple bond as one region of density. So either of those carbon atoms have three regions of density around them, two single bonds and one double bond. So that's a key thing to remember with an atom that's sp2 hybridized. There will be three regions of electron density. The bond angles will be about 120 degrees, and the shape is going to be trigonal planar. Now, what I want to spend a little bit of time in is what is actually a double bond. And this is where our three sp2 orbitals and that unhybridized p orbital are going to come into play. So let's look at a carbon atom here. And actually, I'm not going to draw the bonds quite yet. And we got hydrogen and hydrogen. Now, one of our sp2 orbitals is going to be making a sigma bond here with that 1s. So we'll say this is an sp2 orbital. And here's another sp2 orbital that's overlapping with a 1s. Again, those make sigma bonds because it's a atomic orbital overlapping with a hybrid orbital. Now that carbon is also bonding with the other carbon atom. Well, what is it using to bond? It's got one remaining sp2 orbital, and that's bonding with that one. So there's our three hybrid orbitals. Now I want you to look at the graph above here, or this picture. What is the one orbital we haven't talked about yet? We have not said anything about that unhybridized p orbital. Well, where is that unhybridized p orbital? It's perpendicular to the hybrids. So if you look at the diagram on the right here, here is that unhybridized p orbital. And it is perpendicular at a 90-degree angle to these other sp2 orbitals. Now, if that carbon has an unhybridized p orbital, this carbon over here has one as well, because it has the same type of bonding here. You got an sp2 bonding with a 1s, another sp2 bonding with a 1s, and what's left is that unhybridized p orbital. And each of them have an electron in it. Now, it's hard to see in either of the diagrams that are on this page. But the way that those p orbitals overlap, or I should say, they are close enough so that they will overlap. But they're going to overlap side to side. I know that's kind of not it's very hard to kind of draw and imagine it. But those p orbitals are close enough so that they will overlap side to side. And that overlap there gives us a new type of bond called a pi bond. So what is a double bond? A double bond is made up of one sigma bond and one pi bond. So let's kind of sum all of this up. Adjacent Unhybridized p orbitals are used to make multiple bonds. We saw that on the previous page with double bonds. We're going to see it again when we talk about triple bonds. And pi bonding is side-to-side overlap. So we're going to take these unhybridized p orbitals, and they're going to overlap with each other. And this doesn't have to be just between carbons. This can be between carbon and an oxygen or carbon and a nitrogen as well. We saw this earlier in some examples that we did in a carbon-oxygen double bond. Actually, I'm going to draw this. Let's look at this here. And I'm going to focus just on the carbon and oxygen in the middle. This carbon here is sp2 hybridized. It's got 3 regions of electron density around it. And this oxygen is sp2 hybridized. How do I know that? Well, it's got 3 regions of electron density, 2 lone pairs and a double bond. That's 3 regions of density. And now let's kind of focus a little bit on what makes up that double bond. What I'm going to do is turn this to the side a little bit. So one of our sp2 orbitals is bonding with that carbon on the other side. This sp2 orbital is bonding with that carbon. And then we're forming a sigma bond between the sp2 of carbon and sp2 of oxygen. Now, where this gets a little interesting is what are those lone pairs doing? Where are they? Because you know that electrons have to be in orbitals. So those lone pairs, one of them is in a second sp2 orbital, and the other lone pair is in the last sp2 orbital. Now, all of those, minus the lone pairs, all of the bonds that I've drawn there have been sigma bonds. So how do I get that double bond? Well, I'm going to take the unhybridized p orbital on carbon. I'm going to overlap it side to side with the unhybridized p orbital of oxygen. And that side-by-side overlap forms a pi bond. That's where we get the 1 sigma bond, oops, and 1 pi bond. Now, finally, let's talk about then the last type of hybridization that you're going to need to worry about, and that is sp. Right? We're not going into all the other weird ones that you talked about in general chemistry. We're just focusing on sp3, sp2, and sp. So the way an sp orbital is formed is, again, we're taking our valence shell. We're going to put it in a hybrid blender. Doesn't blend for very long because we only get 2 degenerate orbitals out of it, 2 degenerate sp orbitals, and 2 unhybridized p orbitals. And I want you to think about the implications of that and how you can use those unhybridized p orbitals to make not just a double bond, but a triple bond as well. And we're going to use this compound, ethine, or this is also known as acetylene. And just take a look at this carbon atom here, either carbon, but we'll look at that one on the left. That carbon has 2 regions of electron density. It's got a single bond on one side and a triple bond on the other. When they spread out, they form a bonding of 180 degrees. So that shape is linear. Now let's talk about how that triple bond is formed. I'm going to use this diagram right here. So in an sp hybridized atom, there are 2 hybrid orbitals. Here's an sp orbital bonding with an atomic orbital. And then there's the other sp orbital. It's bonding with the hybrid orbital of the other carbon here. Now, what I should say, what are the orbitals we haven't accounted for yet? We have two unhybridized p orbitals on that first carbon. We have one here that is perpendicular to the hybrids. And then we have a second one here. That didn't show too well. And if each of them has an electron in it, and it's overlapping side to side with the other unhybridized p orbitals on the other carbon, you have, excuse me, pi overlap this way and pi overlap this way. And so a triple bond is made up of one sigma bond and two pi bonds. So let's put all of this into practice. All right, so for each of these, excuse me, we're going to identify the hybridization of all the carbon and oxygen atoms, and then we're just going to count up sigma bonds and pi bonds. So let's take a look at letter A here, and we'll start with this carbon. That carbon, and when it comes to identifying a hybridization, it's simple as just counting the region of density around it. There's 4 regions of density around that carbon, so it's sp3 hybridized. How about this carbon in the middle? Well, it's got 1, 2, 3 regions of density around it. So that makes it sp2 hybridized. Now with the oxygen, and drawing these lone pairs here, oxygen is the same. It's got 3 regions of density around it, 2 lone pairs, and that's that double bond. Remember, a double bond, even though it's got a lot more electrons in it, a double bond is still 1 region of density. So the oxygen is sp2 hybridized. Now for the remaining 2 carbons, each of them have 3 regions of density around them, so they're both sp2 hybridized. So again, that's just finding hybridization is just as simple as counting how many regions of electron density there are. Now, how many sigma and pi bonds are there? Yep, I'm going to erase these so we can just start counting. So with sigma, we got 1, 2, 3, 4. A double bond has 1 sigma in it. 5, 6, 7, and 8. Oh, and these are 9, 10. So there are 10 sigma bonds. Now, whenever you have a multiple bond, you have to account for pi bonds. So a double bond will have 1 pi, and that one will have 1 pi. So there are 2 pi bonds. Now let's look at B here. So again, we're going to look at each carbon, count the regions of density around them. So this one here, 4 regions of electron density. So it's sp3 hybridized. We look at the second carbon. That has a single bond on one side and a triple bond on the other. Same thing with this carbon. These are both sp hybridized. And then this carbon here has 4 regions of density around it, so it's sp3. We would say the same thing for the last one. So now let's just start counting bonds. Again, all single bonds are sigma bonds. So 1, 2, 3, 4. There's one sigma bond here in that triple bond. And then 5, 6, 7, 8, 9, 10, 11. Did I miscount? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, 12. 12 sigma bonds. Now we did have a triple bond. So when we go to that triple bond, remember that there are two pi bonds in a triple bond. All right, let's look at letter C. So again, all we got to do to figure out hybridization is count how many regions of density are around a carbon. So this carbon right here, doesn't matter that it's in a ring, tactic is still the same. There's 4 regions of density around it, 4 single bonds. So that's sp3. We'd say the same thing for this carbon. It's got 4 single bonds around it. That's 4 regions of electron density. Now this carbon here has 3 regions of density around it. 3 carbons, I'm sorry, 3 types of bonds, 2 single bonds and a double bond. So that is sp2 hybridized. And the same thing for this one. Now let's count up some sigma bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the double bond has 1 sigma bond. So that's a total of 10. 10 sigma bonds. And since we do have a double bond is made up of 1 sigma and 1 pi bond. So there's 1 pi bond in this compound. Now, the very last thing, and I know this one has been a little bit long, but we're just going to look at one more thing before we finish. And we're going to look at the relationship between hybridization and bond strength and bond length. The general rule of thumb is that as S character increases, 2 things happen. The bond length decreases and bond strength increases. Now, what do I mean about S character? Well, let's compare sp3 to sp2 to sp. Now, all I want you to do is kind of look at the numbers there. In an sp3, like that's 1s and 3 p's. So we would say that 25% of that is S. And then for sp2, 33% of that orbital is S, because there's 1 S and 2 P's. And then for sp, 50% of that orbital is S. So when we compare these bonds, we're going to see 2 things happen. So in the first example, these carbons are sp3 hybridized. Now the bond length here is about 1.5 angstroms. That's not a number I want you to memorize. Okay, you're not memorizing any numbers here. What I want you to look at is the trend. In an sp2 hybridized, or bond between sp2 hybridized carbons, the bond length is about 1.3 angstroms. And then in sp, the bond length is about 1.2 angstroms. Again, it's not the numbers that are important, it's the trend. As S character increases, the bond length goes down. Now, as far as bond strength, we're going to look at the energy of the bonds. So Be here stands for bond energy. The bond energy for a single bond or between sp3 carbons is 368 kilojoules. Again, I don't want you to memorize that number. It's about looking at the trend because the bond between sp2 hybridized carbons, the energy is 632 kilojoules per mole. And then the bond energy for a triple bond is 820 kilojoules per mole. So the bond strength, or the energy required to break that bond, goes up as the S character increases. So that will do it for this lecture. And when we come back, we're going to take a look at Vesper theory and the shapes of, well, the most typical shapes that we're going to see in organic chemistry.